Hello, AP Calculus AB students, Mr. Record here. We've got another example talking about differential equations. We're going to solve one here that's really not a very complicated one to solve, but it has a little bit of a disguise here at the beginning of it, and sometimes it can throw students for a bit of a loop. If we read the example 3, it says to find the equation of the curve that passes through the point 1, 3 and has a slope of y over x squared at any point xy. Be sure to state the domain of your solution equation. Well, the key to this problem is to first of all recognize that it is indeed a differential equation. And the key is to look at that word slope and immediately be able to translate the fact that slope means derivative, maybe y prime. But the best way to present your derivatives when you're talking about differential equations is to probably use the Leibniz notation. So in this case, you'd say dy over dx. This problem is pretty clearly with respect to x rather than with respect to t because of the presence of x there. So there you have it. That's really the first step that a lot of kids kind of get hung up on, and it's kind of unfortunate because you never really get a chance to show that you can solve differential equations because you don't really necessarily see the differential equation. So that's what we've got for our setup. So very quickly, we then divide both sides by y, and we would multiply both sides by, let's do this right, multiply both sides by dx. So we still have this 1 over x squared on the right with the dx. So now our next maneuver will be to take the antiderivative of both sides. The left side obviously will produce the natural log of the absolute value of y, and the right side will not produce the natural log of the absolute value of x squared. Very common mistake. But this particular 1 over x squared is dreaming of being written as x to the negative 2 because perhaps he's a little easier to integrate that way. X to the negative 1 over negative 1. I want to say that that produces negative 1 over x then, doesn't it? And of course, you can check by taking the derivative and going backwards. And of course, we have a plus c happening after the right side. Now we see that there is an initial condition. So this is an initial value problem. Sometimes we call them IVPs. So we're going to use the ordered pair 1, 3. So 3 will be our y. And of course, 1 will be our x. Negative 1 over 1 is just negative 1. So therefore, we had come to the conclusion that c is just 1 plus natural log 3. I like to write them like that so that it is not confusing what's inside the natural log. So that means that our equation takes on this shape. The natural log of the absolute value of y is really negative 1 over x plus this c of which we speak. Now, remember that the ultimate goal in solving a differential equation is to get that y by itself, if at all possible. And in this particular example, it is at all possible. All we've got to do is exponentiate both sides. Normally, I tell my students not even to write this step out because they could just place a little e base next to the two sides that were already there. Now what that will do is the e and the ln sort of go away. They have an inverse relationship, so absolute value of y is left. And then over on the right side, I am actually going to do something kind of clever here. I am going to take, let's use a highlighter here, why not? I am going to take these two terms, and I'm going to get a common denominator. I'll show you why in a second. That would produce negative 1 over x plus x over x, or negative 1 plus x, or swap it around, x minus 1 over x. And then on the right side, I'm just going to, or the plus sign, I'm just going to rewrite a new base of e separated by a multiplication, because we all know that when you multiply like bases of e, you would just be adding the exponents. Remember, this guy here is just the stuff that's in yellow. So add him to the ln of 3, and that's right what we had up here. The whole purpose in that is that this e to the ln of 3 will become 3 in the next step. Also in the next step, the absolute values go away. Why is that? Well, look up here. we used a positive y to generate this particular solution. The solution of C was definitely linked to the y being positive 3. So y has no fear now of being a negative value. We'll use 3, as we said before, for the e element 3. And we have e to the, and again, I just chose to write this exponent as x minus 1 over x. I want to make sure, oops, I'm going to change this. I'm not real happy with the way that I produced that exponent. I really want to make it look exponent e. There we go, a little bit smaller, lift it to the top like that. And we've got a really good model now. We've got y by itself. We could easily plug in x's and find y, or vice versa. So all is good in the world. Now, as far as what is the domain of this particular solution, well, I think if we look at this a little bit carefully, we'll just ask ourselves, what are the kinds of things that we would not be allowed to plug in for x? Well, it seems like if we were to plug in numbers like a 0, that could be a big problem because we'd have a 0 denominator. But really, anything else that we could plug in for x seems to be pretty legitimate. And in fact, when e is raised to any kind of a power of x, we're going to stay with a positive result, so we're not going to compromise the fact that we declared y to be positive. So the only thing that you have to safeguard here is the fact that x can't be 0. So I'm going to proclaim the domain to be all real numbers except 0. That's okay. I'll write it in set notation using some language. It'll work for us. So there it is. That would take care of this particular example. These two things pieced together would be your final answer. So it seems as if we are convinced that that domain is all real numbers. Well, let's just take a look. Let's take another look at the solution of this a different way. The slope of y over x squared at the point 1, 3. So I'm going to go into the TI Inspire. I've done this for a few other videos. I'm going to go to a graphing scratchpad, and I'm going to choose to change my graph entry to a differential equation. Let's try that again. Change my graph entry to a differential equation. There I go. So I've got my y prime dy dx, whatever, already on the left side, and I know that I want to turn this into y over x squared. Now the Inspire is going to require that I use a 1 subscript for my y's. And then if you recall, the ordered pair, I'll flip back just to make sure, the ordered pair is going to be the point 1, 3. So I'm going to input 1 and 3, and then I'm going to take a look at the solution to this differential equation. I notice that it does go through the point 1, 3. That's a good thing. But I also notice that, whoa, I don't see any values of x over here. I certainly see only positive y's, which that's good because I have absolute value of y. That was sort of eradicated, and I just had positive y. So that probably makes us think that this isn't so accurate anymore, and it's not. And then the reason, I'm going to erase this so that we can modify it, and the reason that it's not, it all hinges back to this ordered pair up here, right? Remember this guy? This guy, it was so important for us to talk about the fact that y was positive, and that would produce only positive y results. But the fact that x is positive as well gives us a completely different handle on our domain. And it turns out that our domain is the set of all x such that x is a positive number. Obviously, x can't be 0, so we will definitely exclude him. But we also know that x has to be positive only. And I'll finish off my little braces here. And that's just a really great way to write a domain here. A lot of times students might just let x greater than 0 be the only thing they write. Nothing wrong with that. It conveys the idea. What I wrote is just a little bit more formal. So there you have it. Don't overthink domains and ranges on these differential equations. It all kind of goes back to the original point that's provided, and that's going to answer your question there. So anyway, I hope this video helps. We'll see you at the next one.